Hello, this is going to be a presentation of my master thesis, which I have defended 2 months ago, and I believe now it is a good time to recall and talk about it a bit more. My thesis is about GPU-accelerated simulation of mass spectra. There's a lot of new terms. I'm going to go through each and hopefully explain what the thesis is about and what was my contribution here. So, my name is Tornik Anoprishvili, and I'm really thankful to my two supervisors, Professor Lasse Lenzo from LUT University and Professor Ernst Witt from Università della Svizzera Italiana. So, what is mass spectrometry? Mass spectrometry is a way to identify what kinds of molecules you have. It is this fridge-sized device. You put it on your tabletop and you pour in some interesting molecules inside it, and what it does is it breaks up these molecules in little chunks, and these chunks then get weighed on a scale, a very sensitive atomic sized scale. Now what you get from a single molecule is this sort of a histogram. Think of it as a fingerprint, and you store this fingerprint into a database. This is what mass spectrometry does. Now, whenever you want to discover a new molecule, you are going to do the following. You're going to put your sample inside the mass spectrometer. It's going to give you some fingerprint, and then you're going to go to this database and look for this similar fingerprint. If fingerprints match, then you most likely have the same exact substance, same exact molecule that you put inside the mass spectrometer previously. Now, mass spectrometry is very expensive, and so there has been a push to make simulations for this. It's very hard to get the materials, the expertise, and the hardware to perform these. Now, QCXMS is this software which allows you to simulate mass spectrometry. However, QCXMS is cheaper than mass spectrometer, but it is still very inaccessible to an average researcher because it requires thousands of CPU hours. So it is more accessible, but not fully accessible to everyone. It needs more CPU hours, and the more it gets, the better the results become. And the inner structure of QCXMS is parallelizable, which means if you have 500 CPUs, it runs in 1 hour. If you have 1000 CPUs, it runs in half an hour. So it becomes faster the more you put in. So here was my idea at the start of the thesis. I said, why don't we use a graphics processing unit which is well known for its parallel performance? Why don't we try to use a single GPU to replace the need for running thousands of CPUs? So the first thing I did is to profile and understand how exactly QCXMS works. When you turn on QCXMS, what it does is it depends on a library called XTB. XTB is a chemistry simulation program. Essentially, it knows how atoms, molecules, and molecular complexes interact. It is written fully in Fortran, and it uses a lot of very complicated algorithms from computational chemistry, and everything in the end is compiled down to a binary file, an Excel file, and you run it on a CPU, or you run it on hundreds of CPUs. That's even better. So this is what QCXMS is. Now, if you look and run a QCXMS, you are going to understand that QCXMS does essentially this. You put inside QCXMS your three-dimensional structure of the molecule. It's essentially the coordinates of every single atom in a long list. QCXMS is going to give these coordinates to XTB, and it's going to ask XTB, hey, what is this molecule going to do right at this moment in time? XTB is going to say the molecule is going to possibly rotate this way. It's going to say possibly these atoms are going to be slightly farther apart. And QCXMS is going to repeat this, what's it gonna do, thousands of times. And at the same time, it is going to simulate the physical things that happen inside the mass spectrometer. So it's gonna say, hey XTB, the temperature of the molecule has increased. What's it gonna do? Then again, what's it gonna continue doing? And XTB, being a very good chemistry simulation tool, is going to tell QCXMS that the molecule is going to break up in some key points. And this works remarkably well. Essentially, QCXMS uses XTB to simulate what happens inside the mass spectrometer. Exceptionally cool. Now, as a programmer, the immediate first step was what happens inside XTB, because that is the core part. And one of the profiles of XTB showed this kind of time distribution. So whenever we run XTB, 71% of all the time is spent on something called self-consistent cycle. The rest of the time is spent on dispersion, Hamiltonian, and the rest of the things, including repulsion and Coulomb interactions. Now, it is obvious that to accelerate QCXMS, we need to concentrate on self-consistent cycle. However, self-consistent cycle is a very, very complicated function. What I mean by this is that self-consistent cycle depends on solving an eigenvalue problem. Essentially, it is a really complicated linear algebra operation. It has some pretty nasty properties which are very hard to translate to a GPU. And so I decided that throughout the thesis, within the scope, it is not really feasible to accelerate this via a GPU acceleration. Next up is dispersion. For the dispersion, I calculated what impact dispersion had for the typical molecules inside QCXMS, and I found that dispersion essentially has negligible interaction. There is no benefit in adding this, so I did not optimize this. Instead, I went for the third part, Hamiltonian. And Hamiltonian does, I'm going to say what Hamiltonian does, but our focus of the thesis of porting some computational load to a GPU is all about accelerating Hamiltonian. So, as I said, everything inside this QCXMS is written in Fortran. Now, I also need to use a GPU, and writing applications for a GPU using Fortran is very painful. So instead, I opted to do something like this. XTB starts as a CPU executable. It uses GPU at some point, and then GPU just hands over the control back to the CPU. Essentially, we have an executable for CPU, an executable for GPU, and there is a jump to GPU and jump back from the GPU of control. And the middle part of the GPU is actually written not in Fortran, but in CUDA C++. So that is the structure. Now, what exactly is this Hamiltonian? Well, the Hamiltonian has to do with overlaps of atomic orbitals. If you remember from the school chemistry, atomic orbitals come in different shapes. The very simplest ones are sphere-shaped. More complex ones have this infinity or dumbbell shape. And calculating how two atoms interact, for example, an atom here and an atom here, we definitely need to calculate their overlap. And of course, what kinds of things overlap? Is this the minus and the plus overlapping, or is this plus and plus overlapping? So calculating these overlap integrals, the volumes between these, is what I have created in this thesis. And that thing is done very, very efficiently with the GPU. I'm going to show why. So suppose we have this two atom system. So we're going to have a hydrogen and we are going to have carbon. I'm going to explain how this is being done in parallel on a GPU. A GPU uses a grid block thread hierarchy of parallelization, which means that when you write a GPU program, you have a three-dimensional grid which is consisting of three-dimensional blocks. Inside blocks there are threads. So grid block thread. There are many ways to fit the overlap calculation between every single shell using this framework. However, I chose to do the following parallelization scheme. Every single shell to other shell interaction is calculated using a single block. A block is parallel and independent of other blocks. And I mean, this is logical because every single shell interacts to other shell independent of the third-party shell. So there are just two shells interacting, and that interaction is fully calculated using a single CUDA thread block. Inside the single thread block, I have 32 threads, and every single thread calculates one aspect of the shell-to-shell integral. Shells are not given as just a single thing. They are consisting of small primitive Gaussians, and calculating the overlap between two Gaussians is the main problem. The most computation is spent on this. A thread handles a single Gaussian to Gaussian interaction. So this is it. This is how the core of the thesis works. And how good is this? Well, it turns out it's very, very good, at least for the Hamiltonian. So here I have set up an experiment where I use quite a beefy system of 32 CPUs, and I compare to that 32 CPU system my implementation. And for calculating a Hamiltonian, we can see that the number of atoms, as that increases, I perform better and better and better compared to 32 CPUs. For instance, I get above 25 times more performance using H100 for calculating the Hamiltonian. And the right-hand side shows us the performance difference when we are doing a Hamiltonian for an alkane. Alkane is this very long chain molecule. It is very regular in structure, and I wanted to see just how big of a difference this makes, the regularity makes. So in here, the GPU processing is over 250 times faster than 32 core CPU. So that's pretty fast. And I compared several GPUs. H100, this is a data center grade, very expensive GPU. RTX 4090, this is a gaming GPU. You can have it inside the laptop. And V100, this is an outdated GPU for scientific computation, and it performs reasonably well, but the best one is H100. Additionally, there is a benefit to using batch processing when dealing with GPUs. So I set up another experiment where I calculate different Hamiltonians for many molecules at the same time in one shot. And for this one, you can see just how much more efficient it is to use a GPU, even for smaller molecules. So if you have a small molecule, simulating thousands of instances of that small molecule with a single GPU is very, very fast. However, there is a major problem, and this requires future work. The major problem is that calculating the molecule's propagation requires many steps. It is not enough to only have Hamiltonian. So it is necessary to transfer data to a GPU to do Hamiltonian and then transfer it back to do, for instance, the self-consistent cycle. And that is where the problem arises. The transfer speed is very slow and it negates most of the benefits of using a GPU. Therefore, in order to make use of this, it is necessary to port other parts of the simulation to CUDA C++ as well. If we do that, then we definitely are able to achieve thousands and thousands of times of speed up over CPUs. Conclusions. So, what I showed in this thesis is that indeed it is possible to use GPUs to replace many thousands, many hundreds of CPUs for simulating MSMS. Batch processing is very scalable when dealing with smaller systems. And transfer overhead is a major problem, and it requires us to port most of the code base from Fortran to CUDA C++. But this is a monumental task. Future work would be definitely to start with this, to begin GPU-only simulations, to port every single piece of logic to a GPU and do end-to-end processing on a GPU. Also to add a fully batched simulation is a very good avenue for future work because small molecules are inefficient for a GPU. GPU requires as much work as possible. And of course, it might be possible to make use of tensor cores. Tensor cores are used for matrix multiplications only. However, it might be possible to use tensor cores, for instance, for transforming the coordinate systems between Cartesian and spherical. And that's one of the main time portions of the current kernel, transforming the two atom system from and to the Cartesian and the spherical. And that involves multiplying by a matrix. So maybe it is possible to use tensor cores for that. However, it is notable that this is mostly memory-bound kernel. We do not have problems with the compute. So, yes, this might be useful, but only time will tell. And this would be the references for the current video. I am really thankful for people who made these tools, especially Professor Grimay and his lab, who made it possible to open source the QCXMS package and the XDB package and the TB Lite, on top of which my work is built. It would not have been possible to do any of this if they had not open sourced their work, and I'm truly thankful for that. Thank you so much for watching. See you next time.